now.
Okay, we can now start. We will today do a continuation of what we were doing last time. Last time we were looking at the complex multiplication method, a method that is used to construct elliptic curves from the scratch. So we'll again look at it, continuation of that in today's lesson. Now, so as I've already said, this complex multiplication method, of course, we'll be using it to construct elliptic curves from the scratch. And the thing is, you want elliptic curves that have properties that you want in terms of the number of points that you want, and the field that you want. So that is why it's then important for you to construct the elliptic curve with those properties. So there are many methods for doing that, but we use the complex multiplication method in our lesson. Now, so very first we look at the steps of doing that, the steps for constructing elliptic curve with your properties that you want, before we look at how to then write the code for doing the same. The first thing you do, because you want your elliptic curve to be in a certain field, so you choose the field you want. Let's say you want it to be in the field F5. So you choose F5. So that is the field you want. Then after you've chosen the field, you then calculate the trace. Now, but before you calculate the trace, what are the properties of the field that you must choose? If you're choosing a field, let's say FQ, where Q in our case is 5, the Q must be such that it can be written as P raised to M, where P is a prime number. So your Q here must be written in the form of a prime number, P raised to M. M is any integer. M is just any integer, but P must be prime. So for instance, in our case, this field can be written in the form P raised to 1. So where M is 1 in our case. Yes, you may want a field F13, and again F13, our P is 13, and our M is 1. But these are cases where M is 1, but we might also have, you may want M to be some other integer. It's not necessarily, it must be 1. Now, so that is what to consider. The first thing you consider while choosing the field, your Q must be one that can be written in this form. Then after that, you then calculate the trace. And the trace, the way we calculate it, you take the number of points you want, the number of points should be equal to Q plus 1 minus T. The number of points must equal to Q plus 1 minus T. So this T, therefore, is what you're calling the trace. And R will be the number of points. Remember, you want to construct this elliptic curve, and some of the properties you want are the number of points you want it to have. So you may have wanted maybe it to have 9 points. just as an example. So if you want it to have 9 points, your R therefore is 9. So you choose the number of points you want. You want it to have 9 points. You also choose the field you want. Suppose you want it in F5. So then you calculate the trace. It will be 5, 9 is equals to 5 plus 1 minus t. So in this case, t will be -3. When you calculate, when you make t the subject of the formula, because this is 6, and 6 will go this side and subtract, that is 9 minus 6. So you find that -t will be 3, and therefore t will be -3. So that is how you get the trace. Now, the trace will then assist us later in writing when we are writing the code. It will assist us later when we are writing the code. So that is the first thing you would then consider. You want to come up with an elliptic curve. So what are the properties you want? One, you want it to have some certain number of points. So suppose you want it to have 100 points. Now you choose the field you want it to be in. So supposing you want it to be in F5. The 5 here, we've said, must be of this, the cube, which is our 5 in this case, must be such that it can be written as p raised to m, where p is a prime number and m is an integer. So that is the first that's the first step you do. The first step you do is to choose the number of points you want your elliptic curve to have and the field you want it to be in. And then you calculate the trace for that. Now, the second step that you want to is to find the complex multiplication discriminant. Now, we shall denote that by D, the complex multiplication discriminant. And you also want to find an integer V. Now, so how do you come up with this D? Remember, you've already chosen your Q above. So your Q there comes in handy here to find D. So first of all, your complex multiplication discriminant D must be less than 0. And then it must be congruent to 0 or congruent to 1 mod 4. So it should either be D must be congruent to 0 mod 4 or D must be congruent to 1 mod 4. So again, that is very important in your selection of Q above. The selection of Q, one of these scenarios must be met. And of course, this one. Now, so how do you find the D? After you've calculated your Q, after you've chosen your Q, and you've calculated your trace, then D will be, you just write this equation and make D the subject of the formula, and V the subject of the formula. So dV, D times V. Now, remember that D is negative. Remember that D is negative at this point. That is why you're saying D must be less than 0. So it's negative. And because of that, we are using the absolute values. So when you use the absolute value, it means -4, for instance, is considered to be 4. And that is why we're using the absolute value. So at this point, after you've chosen your number of points you want the elliptic curve to have, and you've chosen the field you want it to be in, you proceed and find D, the complex multiplication discriminant, and at the same time find an integer V. And this is the properties that will be assisting us to find D and V. These are the properties. And more so this one. More so this. You just write 4 times Q, where Q is the base of the field, is equals to T, where T square, where T is the trace, and then plus d multiplied by v squared. So at that point, you then want to find what the d is. So we shall be looking at an example again, just to emphasize. Now, so we have seen two steps. The first step, remember our task is to come up with an elliptic curve. The only thing we know at this point is that we want our elliptic curve to have a certain number of points, and we want it to be in a certain field. So the first step, we said we choose the field we want it to be in, and then the number of points we want it to have. And then calculate the trace. After you're done with that, proceed and calculate the complex multiplication and calculate V. After calculating D and V, you proceed and find or compute the Hilbert class polynomial. Hilbert class polynomial. And the Hilbert class polynomial, before you calculate it, you must come up with a set of integers ABC. A set of integers ABC. So this set of integers ABC are the ones that will be assisting us to calculate the Hilbert class polynomial. The Hilbert class polynomial of this D, discriminant D. Of this discriminant D. So before we calculate this, we must come up with these integers ABC. Now, to assist us come up with the integers ABC, we consider the following properties. We consider the following properties. The first property is that D that we just obtained in step 2, the D we obtained in step 2 should be written as B squared plus 4AC. So these ones are just assisting us. You know what we know is D. We don't know B, we don't know A, we don't know C. So we want to calculate them from this equation. This is not the only equation that will assist us. The other thing that will assist us is that the GCD of ABC must be 1. And the other thing that will assist us is that this A we want to calculate must be greater than or equal to 1 and must be less than or equal to the square root of the discriminant over 3. So A must be in this range. A must be in this range. It should not be less than 1. It must be, the least it can be is 1. And the maximum it can be is this. So in fact, what you do, therefore, is to get the maximum it can be. Once you get the maximum it can be, then you'll have possible scenarios of the A, what A can be. Possible scenarios of what A can be, and then you may disqualify some scenarios and remain with some scenarios. And we'll be looking at an example just to help us understand that. So I said the best thing here is to first of all get the maximum A can be, and then come up with the scenarios. As you come up with the scenarios, remember the least it can be is 1. The least it can be is 1. So you don't come up with scenarios such that you are considering A to be 0. A can never be 0. A can never be -1. The least it can be is 1. Now, after you come up with the possible scenarios of A, you now want to come up with B. And the B must be the magnitude of B. The magnitude of B must be less than or equal to A. It must be less than or equal to A. So B, there's no scenario where B should be greater than A. At the most it can be A. Now, what if it's negative? What if it's negative? If B is less than 0, that is, if B is negative, then its magnitude must be less than A. So just compare this. This is less than or equal to, and this is less than. Now, so again, let me just explain this point. we've chosen our A. We choose our A before we choose B. So once we've chosen A, we come and choose B. Now, if B is not negative, then it must be it must be zero. It must be zero, but at most, it must be A. At most, it must be A. But if it's negative, then it must be less than A. If it's negative, then its magnitude must be less than A. And again, we shall look at an example. We shall just look at the example. We shall do an example of how to come up with the elliptic curve, and we'll be emphasizing these points again when that time comes. Now, the other condition, well, remember we want to come up with ABC. So the first thing we did, we came up with the A. We will now come up with the B. Once you come up with the B and A, you can now go and obtain C. So remember that C is supposed to be greater than A, or the least it can be is A. The least it can be is A. In cases where B was negative, like this, in this case, where B was negative, then C can never be A. It will always be greater than A. The only time it can be greater than or equal to A is this case. This case where B was less than or equal to A. In a case where B was less than or equal to A, then A can be less than or equal to C. But in cases where B was less than A, now where B was negative and it ended up being less than A, we expect A to be less than C in those cases. Now, so at the end of that, you have your set ABC. And once you have the set ABC, you proceed and find the complex class, the Hilbert class polynomial. And that Hilbert class polynomial, we shall be using our code to do that. So we shall use our code first of all to get us our J invariant and then come up with that polynomial. Now, the next thing, we will project the polynomial to the base field. Project the polynomial that we just come up with here. We then project it to the base field, our field that we want. Remember, we chose the field in step 1. So what we are just doing is that our polynomial would have integers that are larger than the base field. Supposing our base field is 5. Supposing our field is F5. And maybe a polynomial that you're getting is Y. Let me say Y is 7x squared. I'm just giving an example. And 13, let me say X. So what you are now doing here to project what you are doing is that you are reducing these coefficients mod 5. You're reducing these coefficients mod 5. So that's what we'll be doing. So we obtained a polynomial in our step 3. So that in that polynomial that we obtained, reduce the coefficients mod Q. Reduce the coefficients mod Q. So that is what we then call projecting the polynomial to the base field. Now, after projecting the polynomial to the base field, what we want is using our Rust code, we want to find our J invariant. And this J invariant, let's call it J naught. So that is the root. Those are the roots. In some cases, it will just be one value. In other cases, more than one value. And we shall look at examples of both cases, where it is one value, and another example where it's more than one value. Now, once you have this J invariant, you now choose the cases. So we have cases of elliptic curves depending on the J invariant you obtain. Depending on the J invariant that you obtain, we have different cases of elliptic curves. So you choose the elliptic curve that is appropriate for your J invariant. So what are those cases? Let me just share the cases. The cases for the J invariant that you obtain. So if your J invariant is not equal to 0 and is not equal to 1728, then your curve will take this shape or this shape. So you can choose this shape and then use, first of all, choose this shape. Then after you've chosen this shape, find how many points this curve has. So if you find that this curve has the number of points you are looking for, then this is the curve. Your curve becomes this. You just substitute C1. Just substitute C1, and I'll be showing you how to get C1. Now, if you find that this one does not give you the number of points you want, try this other shape. And what I'm saying is, if your J invariant is not equal to 0 and is not equal to this, then your curve must be one of these, not top, not all of them. It could be one of these. It's one of these. So you just try each one of them and see which one gives you the number of points you want. If you find it's not this one, then try this. Of course, you'll find that if this failed to give you the number of points you wanted, then this one will give you. This one will give you the points you wanted. Now, that is a case where the J invariant is not equal to 0 and at the same time is not equal to 1728. Now, what about if the J invariant is 0? And if it is 0 and is not equal to -3, if it is 0 and is not equal to -3, no, the J invariant, if the J invariant is 0 and your discriminant, the CM complex multiplication discriminant you calculated above. Let me just repeat. You've done using your Rust code, and you found there's a case, the first case, you found that you did your Rust code, and you found that your J invariant was not equal to 0. And at the same time was not equal to 1728. Then your code, your equation of the curve would either take this shape or be this, one of those. Now, let me say this was not your case. Let me say this was not your case. So you did not find, your J invariant was not equal to 0. Let me say it was 0. So if it was 0, now check the discriminant you got above. If the discriminant was not equal to -3, then your elliptic curve is supposed to take this shape or this shape. So you just take this, for instance, and try and see whether it has a number of points you want. If it does not have the points you want, then this one must be the one. You can try it and check. You will find out that it has the points you want. So that is the second case. That is the second case. And the second case here, your J invariant was 0. And the discriminant was not equal to -3. What about a case when your J invariant again is 0, and your discriminant now, this time, is -3. If that is the case, you will choose from these curves. You're either choosing this or that or this or this or this. And now you're not just choosing, you're trying each one of them and seeing which one has your points you want. Because when you began constructing this elliptic curve, one of the properties you wanted is that you wanted, for instance, a curve that has 100 points. So you're not trying and seeing, you are not trying to see whether this one has 100 points. If it doesn't, try this. If it doesn't, try this. If it doesn't, try this. At the end, one of them would have the number of points you want, or even two of them, there's no problem. But what you're saying is, among these, there must be one that has the points you want. If this was your J invariant and this was your discriminant. Among these, one of them must have the points you want. So you just choose which one from this. Now, that is the third case. The fourth case is now this time, let's say your J invariant is 1728. If you remember what was the first case? The first case was, it was not this and it was not this. And then we came up with another case. What about if it is 0? If it is 0, then we check the discriminant. Now, if it's 0, we check the discriminant. Check the discriminant. If it is 0, the J invariant is 0, check the discriminant. Is it -3 or is it not? What about this case? Now the J invariant is 1728. The J naught is 1728. If that is the case, check the discriminant again. Check the discriminant. And again, check the discriminant. There are only these cases. These are the only cases you have for the elliptic curves. Elliptic curves would meet one of these cases. One of these cases. So the cases, we're just looking at the J invariant. And remember, the J invariant, you are doing it using your Rust code. That is what that is the only point we are using the Rust code, just to give the J invariant. And once you have the J invariant, you looking at the cases. So the J invariant would be either 0 or not 0, or would be 1728 or not 1728. So if it's not 0 and is not 1720, so that means something else. Something else. There's only these two cases to consider. Now, where it's 0, the two cases when it can be 0, we check the discriminant. Is it -3 or is it not? If it's not -3, these two cases, these two scenarios. If it's -3, these how many scenarios? 6. There's 6. Yeah, these 6 scenarios. One of them would work for you. Now, what about if it's 1728? Again, we have these two cases. Either this, check the discriminant and see which option works for you from this. Check which options work for you. Now, so we've been checking the option, and that is what we've been saying, or that is in fact our next point, which says verify the order of the curve. That is what we've been doing. Every time we got our J invariant and compare, we chose the elliptic curve. And after choosing the elliptic curve, we substitute our C1 and C2. I'll be showing you how to get C1 and C2. And then you check the order of the curve. You check the order of the curve. You're checking whether it has the number of points you want. If it has the number of points you want, that is the curve. And then that becomes the curve you're looking for. So let's again look at an example. Now this time, just trying again to emphasize those steps. Let's look at an example. Now, so assume now you want an elliptic curve. Of course, we know this elliptic curve. We know it's y square is equals to x cubed plus x plus 1, where our a is 1 and our b is 1. But let's assume we don't know. Let's assume we don't know this curve. We don't know the equation. So it's this equation that we want to come up with. Let's assume we don't know it. But let's assume also, okay, we know this elliptic curve has 9 points. And it has been done, in our example, it has been done on the field F5. So we want to assume we don't know this equation. And we want to say that we want to construct it. We want to construct this elliptic curve. So what do we do in our first step? We choose the number of points we want. So we've chosen 9 points. We want an elliptic curve of 9 points. Then we choose the field. On what field do we want it? We want it on this field. So let's begin with these two and see that we come up with this equation. So that is what we want. This equation is what we want. Let's begin with these two conditions. So these are the conditions we want our elliptic curve to meet. So those are the properties, therefore, we want our elliptic curve to meet. So the first property, the first step, in our first step, we say the first thing we do, we choose the field. We know the points we want. We want it to have 9 points. So we choose the field. So once you've chosen the field, the next thing we say, you calculate the trace. So you calculate the trace, you just say 9 is equals to 5, where 5 is the base of the field, a plus 1 minus t. So this is the order of, this is the number of points. So if 6 were to go the other side, you have 3 is negative t, which will then mean that t is negative 3. This is your trace. Now, once you have the trace, the next thing we said we go straight to find d, the discriminant. We go to find d, our discriminant. That is the next step. So we want to go until we get the equation of this curve. Remember, we know the condition we want, an elliptic curve. We are imagining we don't know the equation here. We don't know the equation of this curve. But we know we want a curve of 9 points. We also know that we want it to be on F5. So the first step is we find our trace. We found our trace. Then we come and calculate our discriminant. The condition was that the discriminant is supposed to be less than 0. It's supposed to be negative. The other condition was that the discriminant should be congruent to 0 mod 4, or should be congruent to 1 negative 4 mod 4. This one should not worry anybody. This one should not worry anybody. Once you do this other condition, because there are 4 conditions, 1, 2, 3, 4. Once you are done with this 4th condition, these others will just follow. These others will just follow. So they should not worry anybody. So let's look at this condition. That 4 times q should be equal to the trace plus the discriminant multiplied by v. So we want to find the v. Okay, so our q in this case is 5. And our t we had found -3. So 5 times 4 gives you 20. And then -3 square will be 9. So this is 20 is equals to 9 plus d multiplied by b square. So 9 goes the other side, you would have 11. You would have 11 is equals to d multiplied by b square. Now it's from this point that we now want to check what values can d take and what values can v take from this equation. So let's just look at it together and see what can be our d here and what can be our v. So from here, just reason from this equation. We've seen how 11 has come up. 11 has come up, this is just 9. Went to the other side, you get 20 minus 9, that gives us 11. And then we remain with, on the right side, we have d multiplied by b squared. So the question is, what is our d? Because it's d we want to come up with, then b. Now, for this case, and this will not always be the case, this will not always be the case, but for this case, you can see that the number here is prime. The number here is prime. So the number prime can only be written as, this 11 can only be written as 11 multiplied by 1. Multiplied by 1. That's the only way, because this is a prime number. You cannot find two numbers, because these are two numbers. These are two numbers, b square and d. So we want d multiplied by b square. Give us the number on the left. But the number we have on the left is a prime number. So it can only be written as 11 times 1. 11 times 1. Now, of these two numbers, one of them is d, and another one is b squared. So the one that must be b squared is the one whose square root you can get. The one whose square root you can get. In our case, you can get the square root of 1. So that means that d therefore is 11. That means d is 11. So if that is the case, then now what is our v? Our v will then be plus or minus 1. So when you reach here, it's just trying to check your equation and seeing what can v then become and what can d then become. So that is the reasoning. That is the reasoning I used here. But now this is what we've got. This is what we've got. So we want to look at the other condition. The other condition now, let's come to the other condition. D is supposed to be less than 0. So that means our D therefore is -11. Because here what we are getting here was not D, was the magnitude of D. The magnitude of D was 11 at this point. The magnitude of D was 11, and then V square was 1. So the magnitude of D means it could be negative or positive. So whatever is inside the modulus, could be negative or positive. So since we need this, we need D to be less than 0, so we take D to be -11. We take D to be -11 because of that condition. Now, if you check the other condition, you would find it's satisfied. The other condition was that D must be congruent to 0 mod 4, or if that is not the case, then it must be congruent to 1 mod 4. So let's see. This negative 11. What is negative 11 mod 4? So since this is negative, you add 4 to it several times until you get a positive number. So negative 11 plus 4 will be negative 7. Then negative 7 plus 4 again, that will be negative 3. Then negative 3 plus 4 again, that will be 1. So it's true. It's true that D is congruent to 1 mod 4. So you now have D and you have V. And the good thing is just look at how we got D. You're not calculating D actually. You're not calculating D. What you are doing is you come to this last equation and you're just thinking from this last equation, I want the number on the left to be a product of 2 numbers. This is the last equation I'm referring to. So you come to this last equation and the thinking should be that I want the number on the left to be a product of 2 numbers. And one of the numbers must be a square. And then the other one is D. So if you have 11, and 11, lucky enough, is just 11 times 1. Also 11 is prime. So one of these numbers must be a square. One of them must be this square. So one that you can get the square root easily. One that you can get the square root. Okay, I'm not saying that this number may not have a square root. Sometimes it could have, depending on the field you're working in. Depending on the field you're working in, it could have a square root. So again, at this point, you may want a code, may want to have Rust code that gives you the square root in some fields, given some fields. So 11 could have a square root, but for this case, it doesn't. For this case, in our case, it doesn't. But in some field, it might have a square root. So in cases where the number here has a square root and the number here has a square root, which one do you choose to be V square and which one do you choose to be D? Now the one you choose to be D and V square, okay, the one that you choose to be D will be one that fulfills the first condition, that D should be less than 0 and the D should be congruent to 0 or congruent to 1, mod 4. So one that gives you, one that fulfills this condition is that the one that you take D to be D. They may not all of them fulfill this condition. They may not all of them fulfill this condition, but if they fulfill, then that means you use trial. Try this. If it accepts, try that, and so on. That is, of course, what you are doing in this code. And this, you need to be trying some cases. You're trying this case. If it doesn't work, you try this other case, and so on. Now, good. What have we done? We've we chose our field. We are just, I'm trying to recap what we've done in this example. In this example, what we've done, 1, we chose the field, F5, and 2, we want our elliptic curve to have 9 points. So the first step, with those 2 conditions in mind, we calculate our trace. After calculating our trace, we proceed and calculate our D and V. Now, so the other step that we said was to compute the Hilbert class polynomial. Compute the Hilbert class polynomial. But to compute the Hilbert class polynomial, we had several conditions. I've not listed them here, but let's just go back and see what the conditions were. The conditions were that first of all, we come up with a set comprising of ABC. A set comprising of ABC. That was a condition, what we did. Just taking you back there, I did not list it here. Here it is. To compute the Hilbert class polynomial, the first thing come up with a set comprising of ABC, and the set will be of this, should meet these conditions. But what did I say? What did I say? The first thing you do here, don't begin with this or this or this or this. Begin with this one. Begin this part. Find A first of all. Find A first of all. After finding A, come to this. Find B. After finding B, come to this and find C. Come to this and find C. So we begin with this. So to begin with this, I say at this point, find the maximum A. Find the maximum A. So in our case above, just do it here. We found our D to be negative 11. So what is our maximum A? Our maximum A, I'm calculating this part here, this part, should be the square root of the modulus of 11, which is just 11. Modulus of 11 is just 11, divided by 3, the square root of that. So at this point, you can use your calculator. Yeah, let me just look for my calculator. Okay, so I have the square root of 11 divided by 3. That's let me write it properly. Square root of 11 divided by 3. I'm getting a number 1.91. That is enough. That is enough. You don't need to write all of it. But what I'm getting to understand is that A is less than or equal to, no, it's greater than or equal to 1, and it must be less than or equal to 1.91. This A must be an integer. Must be an integer, not, this is not an integer. So that means it must be a whole number. That's what I mean. It must be a whole number in this range. The only whole number in this range is 1. The only whole number in this range is 1. There are cases where we would have several whole numbers in this range, as the next example would be, and I'll show you then how we settle at A. In our case, it's very easy. You only have one whole number. So A, therefore, is 1. A is 1. We've already obtained A. And look what we did. We found the maximum value A can be. And then we're understanding that it must be in the range. It must be in the range, this and that. And we found this value to be 1.9. So we are asking ourselves, what are the possible values of A that make it A positive? So A is positive in this range. The only A that is positive in this range is 1. So A is 1. Once you've obtained A, now obtain B. Now obtain B. We've settled on A being 1. Now obtain B. We've got the next condition. The next condition. I said there's an order we would follow. I said the order is we would do this, then come to this. Now, this case does not, okay. So B, the modulus of B should be less than or equal to A. So that means B is likely to be 0 or 1. Because A is 1, and we are saying that B should be less than A, which is 1, should be less than 1 or should equal to 1. The maximum it can be is 1 because A is 1. The maximum it can be is 1. So we're not saying that B is all of this. We are saying that B is likely to be one of these. In some cases, it can be all of them. So we will just check to see whether it's all of them or it's one of them. So, but this is what we say at this point, that given this condition, and given that our A is 1, B is likely to be 0 or 1 based on this condition. Now let's try the first scenario. Let's check whether it's possible that B can be 0, because we must settle on one of them or both. But they must meet all the conditions. Now let's check whether B can be 0. What does it say? If B is 0, then its modulus must be less than 1, must be less than A. If B is 0, its modulus must be less than. That is true. That is true if we take B to be 0. If we take B to be 0, its modulus will be less than A. There's no problem. That condition is met. Now, but we are not saying that B is 0 yet. We have to check here. You have to check whether if B is 0, can you obtain C? So we come back here. We come now to this condition. Want to see if B is 0, can you obtain C? So we just try. We know what D is negative 11 is equals to B 0 minus 4. A is 1, then times C. So that means negative 11 is negative 4C. And remember that negative 11 here is a prime number. And then we have C here. Okay, so what is C? C is 11 over 4. C is 11 over 4. Now, so you see, C must be an integer. C must be an integer in our case, because this set is made of integers. But what we are obtaining there is not an integer. So it means that B cannot be 0. It means that B cannot be 0 because C is supposed to be an integer. So we then try this other option. We must obtain C. So let's try this other option. What about if B is 1? Can B be 1? B must, one of these must be 0 or 1 or both. But we've already disqualified it from being 0 because when we tried to find C, we did not find an integer. We did not find an integer C. Now, what about if B is 1? D was negative 11 and B is 1. Negative 4 C, because A is 1. So this one comes this way to be negative 12, is negative 4C. So in this case, our C is 3. It's an integer. Our C is 3. So we then settle to A being 1, we settle to B being 1, and we settle to C being 3. We've obtained our set ABC. And you can see how we came up with A, how we came up with B, and you don't just settle on all of them. You have to see, after you come up with the possible scenarios, the likely B. After you come up with the likely integers that are supposed to be, you check which one will give you C. That is the one you settle on. Good. So we've after that, you now want to calculate or compute the Hilbert class polynomial. Hilbert class polynomial, and this is our step 3. And the step 4 after the Hilbert class polynomial will be reducing that polynomial. The coefficients of that polynomial will be reducing the mod 5. Reducing the mod 5. Those are the steps. And then after that, we will then jump to our code and get the J invariant. Now, so we had reached this point. And at this point, I'm just explaining how the procedure, and I've just done it in the procedure. I've said, first of all, obtain the maximum A, and so you get the maximum of A is that. And then what are the possible values of A? So A will be in the range. A will be in the range of what was A? The range of A. A was it? It was supposed to be the less than, greater than. Yes, supposed to be. Yes, supposed to be this. Then maximum. Okay. So then we settle on A being. We settle on A being 1. Okay. So here I had used 0 here. So when I used 0, that is when I came up with the likely set. But of course, it's supposed to be 1. It's supposed to be 1 and not 0. And of course, when I thought of 0, 0 would not work, because if A is 0, then it meant that B will then be 0, and if B is 0 again, it never worked. So our A is 1. Our A is 1. What about B? You come up with the possible scenarios of B, and then you disqualify some. You disqualify some, those that will not give you an integer for C. Those that will not give you an integer for C. So we arrive at C being 3. When B is 1. When B is 1, C is 3. You've already seen how to do that. Now, once you have your set 1, 1, 3, where A is 1, B is 1, and C is 1, C is 3, and you have your discriminant as negative 11, you proceed and calculate the polynomial. And to calculate the polynomial, the first thing you do is, the formula is J naught plus D out of 2, it's supposed to be 2I, 2, 2A. No, it's just 2, because we don't know what A is. It's just 2. Now, so in our case, then this is what we do. This formula, I put it somewhere. I think I don't know what I included in our notes. I included in the previous notes, so this one I did not include it. But it's a formula for getting the polynomial. The formula for getting the polynomial, I did not include it here. I included in the last in the last lesson. Now, so the square root, the square root of 11 negative, the square root of negative 11 is the same as the square root of 11 times negative 1. It's the same as that. Because you cannot get the square root of negative 11 just like that. This is a complex number. This is a complex number. So then it will be the square root of 11 times the square root of negative 1. But the square root of negative 1 is I. The square root of negative 1 is I. I is an imaginary number. So that is why you find the square root of negative 1, I've written it as I, the square root of 11. I square root of 11. This is how I get it. This would be I, and then multiplied by square root of 11. So that's why you find it. That's how you find this. So this is how you calculate the Hilbert class polynomial. It's supposed to be x minus j into this, minus j into this. But now this is the part we want to go into our calculation of the j invariant. Calculation of the j invariant. You cannot do this manually. So what we do, we use our Rust code, and we want to see what our Rust code gives us to find the j invariant. So after you've gotten the j invariant, we'll come and plug it here. It's supposed to be x minus the j invariant. X minus j invariant gives you the Hilbert class polynomial. So this is what I'm calling the Hilbert class polynomial. And once we have this, we would then reduce this mod 5. When you reduce this mod 5, you get 3 as the remainder. You get 3 as the remainder. And that's what I've just done here, reduced it to mod 5. Now, so it's this Rust code that I'm interested in. How do we write it so that we can have our j invariant? So let me just share the Rust code that I have. Then later on, I'll explain how it works. Okay, it's not this one. Yeah, it's this one. Now, so this is a Rust code. It's a very short code. And I've told it, let the square root of 11 be this. 11 times 11, the square root of the 1 in the bracket. So the 1 in the bracket is 11. So just get the square root of that. Then let tau a complex negative 1. Okay, so this is just a formula. This is just a formula that we had, which was, negative, the square root of negative 1, 11. No, it was negative 1. What was this? The formula? The formula was negative 1 plus the square root. So negative 1 plus the square root of negative 11. Everything divided by 2. Everything divided by 2. So this is just the formula I've written here. But I have told it it's complex. because negative 11 is the square root of that is give you a complex number. And so because of that, you have to import num complex just to assist you with the square root of a negative number. Then the formula for doing that is what we call the J approximation. So this is a J approximation. I will not go into the details of how you approximate J. But it's J approximation, and you can see at the end of it, I've asked it to round off the figure to give me a constant figure. Of course, it will be approximating. Then after approximating, it gives me a constant figure. So if I run it, I get negative 32, 768. Negative 32, 768 as the J invariant. Negative 32, 738. I want to carry it to our equation. I want to carry negative 32 towards negative 32, 7. Yeah, so what I have is this. It is x minus negative 32, 768. And this minus and this gives you a positive value. Now, this is now what we call the Hilbert class polynomial. And as I said, once you obtain it, we reduce it to mod 5. And when you reduce it to mod 5, this is what you arrive at. Now, we've calculated our J invariant, and we found, okay, we found this. After finding this, we now want to find what x is. What is the value of x? And we are doing it mod 5. What's the value of x mod 5? So that means to get x mod 5, we just equate this to 0 or to 5, because mod 5 is the same. 5 is the same as 0. So when you do this, you find that x will be 2. X will be 2. And so therefore, that is our J. Our x is 2. Therefore, that is our J. So the J, this is how we calculate our J. The one that we want to go and then choose the scenario for the curves. Remember, our scenarios. In our case, J is 2, so it's not equal to 0. And you can also see that this J is not equal to this. So if that is the case, you calculate C1. At calculate C1, you have J naught out of 7. This is just a formula that is used to calculate C1 minus J naught. So it's J naught out of 1728 minus J naught. So J naught in our case is 2. So it's 2 out of this. Now this number, you can reduce it more than 5 because it's bigger. So when you reduce mod 5, this is 3. So it's 2 out of 3 minus 2. 2 out of 3 minus 2, which is just 2. So our C1 is 2. Now, why are we calculating C1? Why are we calculating C1? We're calculating C1 because we've seen that our J naught is 0, not equal to 0, and is not equal to this. So our choices for the curve are here. Condition case 1. The first case, when J naught is not equal to 0 and J naught is not equal to this, we said our curve would take this form or take this form. Our curve would take one of these forms. So look at this first form. We need the C1. We need the C1. So we want to, first of all, test this form. If it fails, then we will calculate C2 and check this form. If this one fails, then this one will accept. We want a curve that will give us the number of points we want. Now we've just calculated C1 and obtained 2. And our J naught was not equal to 0, J naught was not. So let's try this form. So y square would be x cubed plus C1 is 2. 2 times 3 will be 6. Remember, we are doing it mod 5. 6 mod 5 is 1. And then 2 times 2 will be 4, because C1 is 2, then times 2 will be 4. So we arrive at this curve. We arrive at this curve. This is the curve we arrive at. Now, this curve is the one we are looking for. The only difference is that it has a 4 here. So I'll show you how this 4 then is converted to 1. But before that, with your Rust code, when you try this, you will find this curve has 9 points. And you wanted a curve that has 9 points. You wanted a curve that has 9 points. So you already have it. You already have it. But this is not the one we use. So after obtaining this, you now do what we learned earlier, and it was called isomerism. So want to map this curve to another curve. So that is what we do. We want to map. So this is a curve we obtained. This is a curve we just obtained when we substituted our C1. But now in practical reasons, in practical applications, we will not use this one. We will not use this one, but we want to map it to the curve that we want. The curve that we want to map it, this is how we map it. So the curve that we will now obtain should be equal to A. In our case, A is 1 here. In our case, A is 1, but now multiplied by D square. And B in our case is 4, but now multiplied by D cubed. But how do you obtain D? How do you obtain D? We had done this earlier. We had done this one earlier in one of our lessons. When you are doing mapping a curve to another curve, when you map a curve to another curve. So when you do the same way we had done earlier, you would find that D is 4. D will be 4. Given a formula, I'll give you a formula later. But D is 4. How do you get D? D is 4. We had done it earlier. I'll write for you the formula. So D is 4. 4 square will be 16. Mod 5, 16 mod 5. To go there 3 times and the remainder will be 1. The remainder will be 1. And then this is 4 cubed. Remember, 4 squared is 1. 4 squared is 1. But we are taking 4 cubed times 4. 4 squared is 1, so this is 1. What have I written? It's supposed to be 4 times 4 cubed. Yes, so this is 1 and this is 1. So 1 times 1 again will be 1. So this is the curve we began looking for, and we've arrived at it. That's the curve we began looking for, and you have arrived at it. So what we did here was just isomorphism. We call it isomorphism. What do we call it? When we are mapping a curve to another curve. Mapping a curve to another curve, and the formula for D was given. Now, so I can see because of time, because I wanted to look at this other example. These are long examples. And this other example, we know what this elliptic curve is. We know that it's y square is x cubed plus 8x plus 8. But we want to assume we don't know it, and so we want to look for it. But one thing we know is that it has 20 points, and that it is on the field F13. It's on the field F13, and it has 20 points. So this is what we want to begin with. These are the properties you want. You want an elliptic curve that has 20 points and is on F13. This one we don't know, but we will obtain it at the end. It's what we are looking for. So the first thing you do, as you've done, is you get the trace. Get the trace, the number of points. The number of points, 20, should be equal to 13 plus 1 minus t. So this is 14. Take the other side. You have 6 is minus t, so that t is -6. So our trace is -6. Now, once you have the trace of -6, calculate d. Calculate d, our complex multiplication discriminant. There were some properties that d must satisfy. The first property is that d is supposed to be less than 0, and that d must be congruent to 0 or congruent to 1 mod 4. So this is just a formula, and it applies for all elliptic curves. Now we have our t, and this is another condition it must meet. So this is the condition we used last time. Take formula by q. Our q in our case is 13. Our q in our case is 13 because we are doing it on F13. So 4 times 13 should be equal to t squared, then multiplied by d, then multiplied by that. This is 52, and this is 36. Of course, this one can come this side, and you have 16 is equal to this. Now, so what is d? At this point, again, we want to reason what d can be. What d can be. At this point, again, is just reasoning. And so look at 16. Our 16 should be written in as a product of two numbers. Of course, we can write it as this. Of course, you can also write it as this. Of course, you can also write it as that. Now, which of these cases would give us D and give us V? So V must be a number, V square must be a number that is a square. We can see this number is a square, this number is a square, this number is a square, and so on. So we have several options. So which one do we settle on? But at this point, as I said, we just reasoning with these numbers, and of course, we're also reasoning with our field. We know the field is F13. So which numbers would have a square root? So these are the options I've said. This gives the solutions will be this -4 for D and plus or minus 2. This one I think I've already chosen. I've already chosen. So remember the option of 16. Let me just again write the options here. The options here were 16 can be written as 4 times 4. 16 can be written as 8 times 2. And 16 can be written as 16 times 1. So we want to choose D. But now look at this. I can disqualify this because, for instance, D cannot be 16 because there's no way 16 can be congruent to 0. No, it's possible. It can be 0 mod 4. So that could not be the reason to disqualify it. Because it can be 0, congruent to 0. So we cannot disqualify that. So I think we can choose this and choose that. Choose this and choose that. So that going forward, we'll now see which one to disqualify with what reason. So the possibility is D can be 4. D can be 4. And if D is 4, B square can be 4 again. So that V therefore is 2 plus or minus. So D can be 4. And V square is 4. I'm just looking at this. V square is 4. So if V square is 4, then V is the square root of 4, which is plus or minus 2. So that is one way. I've chosen that. And the other way is this one. D can be 16. Also, we've just seen that 16 mod 4 is 0. And V square can be 1. So if V square is 1, it means V is plus or minus 1. So again, we have this scenario. So we have those two scenarios. So we want to move with them and see if all of them would hold, or if some of these two will be disqualified. We move with them. Because at this point, we've not disqualified any of them. Now, let's take the first scenario where D is -4. And then, what is J? And again, we will use a code. We will use our code to find what J is. We'll use our code to find what J is. Now, when you do using a code, you will find that J is 1728. Now, so if D is -4, like in this case, and J is 1728, you come back here and you choose the curve that is in that category. The curve that is in that category, where D is -4, just come back here. D is -4, and J is 1728. This is the category where D is -4 and J is 1728. So that means your curve could be one of these. Your curve could be one of these. So you calculate your C1, calculate your C2, calculate your C1, calculate your C2, and try. For you to calculate the C2, first of all, you calculate the C1. You don't begin by calculating C2, you calculate C1 first. Okay, so I think because of time, you can stop there, but I'll share these notes so that you look at it. And then if you have a problem, we can again discuss it. I've shown how to calculate. Okay, this one you're using a code. I'll be sharing that code to find your J invariant. The code, I have it, the same code. It's the same code that we had before. And that same code will then be giving you, I don't know whether it's this one. No, it's not this one. That's the same code. I just modified I just modified the bottom part to give me, because I discovered this one was giving me two J invariants, J1 and J2. So you can see one of the J invariant is 1728, and the other one is this one. So you then do for both. You find the curve for this and then for this. And then I've explained in the examples. So you just go through the examples and you go through this code and see how to write the code. I think we should end there. Thank you.